Hello everyone. Today we'll understand about the experiment number 6 in our communication laboratory, which is study of microwave test bench. So this particular experiment has two parts, say part A of the experiment and part B of the experiment. Aim of the part A experiment is to determine the frequency and measure attenuation, whereas in the second part you will be determining lambda g, that is guide wavelength, and voltage standing wave ratio, VSWR. Okay, so this is the aim of 6A and 6B. Now before jumping into the actual procedure of what we are going to conduct and measure, we have to understand what is microwave and then what is a microwave test bench, correct? So let me first explain microwave test bench, then we'll uh, revise some of the topics which you have already studied in your MWA course, correct? So microwave test bench is used to study microwave characteristics like guide wavelength, free space wavelength, cutoff wavelength, or in the other way the different frequencies, that is free space, guide, cutoff frequency, then voltage standing wave ratio, attenuation, isolation characteristics, and study of directional couplers. So for all these applications or all these measurements, we are going to use microwave test bench. Okay. Now coming to the microwave signals. So microwaves are defined with the help of electromagnetic spectrum. So we need to know what is electromagnetic spectrum. It is the range of frequencies or wavelengths which exist in nature. The different kinds of signals what we have, they have been divided into different frequencies, and thereby you can say different wavelengths. And that division, that is the arrangement of these from say a minimum value to a maximum value, is what our electromagnetic spectrum. So here in this range you can see the signals which fall under this range are called as microwave signals. So what is this range? This is actually 300 megahertz to 300 gigahertz, or equivalently we can call 1 meter to 1 millimeter. This is the general description. So the signals which are having a wavelength between 1 meter to 1 millimeter or frequency between 300 megahertz to 300 gigahertz are called as microwave signals. This is purely for our application. We have defined these are the frequencies. In some of the applications, 30 megahertz is also considered as microwave signals. Okay, this is the range of frequencies in which the signals whichever exist are called as microwave signals. The name microwave is just symbolic, saying that the wavelength of these signals is very small. Either it is in the range of millimeters or maximum it is meter. Whereas you can see some of the frequencies. If you have a frequency of this one, that is 100 hertz, its wavelength will be 10 to the power 6. So if you see this, you can understand the difference what we have for 10 to the power 6 and 10 to the power 0, that is 1 meter or 1 millimeter. Comparatively smaller wavelength. That is what the indication we are using for microwaves. Okay. Now again in these microwaves we have different bands of frequencies for different applications. So this is the different band of frequencies. As I have told, this is purely different authors will define different range, but acceptable range is from 300 megahertz from here to 300 gigahertz. So the bands, if you go through, ultra high frequency, L band, S band, C band, X band, KU band, K, KA, V, W, and millimeter band. So in our lab, what we are going to do is we will be generating frequencies between 1 to 2 gigahertz for our antenna experiment and the study of different microwave devices. Whereas the test bench experiment involves the frequency in the X band. That's why we have listed out these different frequencies inside the microwave frequency range. Okay, and again you need to note that microwave signals are having number of applications, say starting from radar, mobile communication, Bluetooth, Wi-Fi, satellite communications, very importantly microwave ovens. We can list hundreds and thousands of applications like this for the microwave frequencies, correct? That's why what we are going to do is, in this particular experiment, we are going to see the generation of microwave signals and propagation of these microwave signals through waveguide and other different components, and then measurement of the different parameters of the particular microwave signal generated. So that is the flow what we have. Now let us see another important concept, which is about waveguides. So what is an waveguide? Waveguide is a kind of transmission line. So what are the transmission lines? Transmission lines are the conductors which carries the information or power from one end to another end. Examples of these transmission lines are coaxial cables, two-wire telephone lines, likewise we can say waveguides. So what might be the difference between these coaxial cable, two-wire telephone lines and waveguide? The difference is these coaxial cable and two-wire telephone lines are designed to have an center conductor. If you see a wire, this will be a coating. Inside this, there will be a conductor. So outer shield or outer plastic cover will be there like isolator and a protector. Inside that you will be having a center conductor which carries the information in both the cases, but in different manner. Okay, but in waveguide we have hollow structures like this. You can see different types are also given, but they are metallic hollow structures with no core conductor. They are hollow inside. So how signal passes? Signal passes through multiple reflections through the surface of the waveguide. So in this way, that's why these waveguides are completely different from the coaxial cable and other types of transmission lines, wherein they are particularly used for microwave signal transmission. So why they have been designed like this instead of using coaxial cable or any other center conductor. It is because the center conductors what we use, they actually attenuate more energy. Since the microwave signals are having very less power, they easily get attenuated uh, as the distance increases. That's why we need to have a minimum attenuation from the conductor side. So to achieve that, these kind of waveguides have been designed. Okay, so this is to carry the microwave signal from where to where. For that, we can consider an example. Say you are generating microwave signal here and you want to transmit it from antenna to source. This is the generator, this is the antenna. So in between this, these waveguides can be connected to transfer microwave signal from this point to this point. Just like you have a dish TV in your home, the dish antenna uh, will be receiving the signal, and through a cable it will be sending the signal to your television. So this is your coaxial cable. Likewise, you will be having the waveguide, which will be like an interface between the source and the antenna at the transmitter end. At the receiver end, it will play a reverse role. It will receive the signal from antenna and feed it to the destination or some kind of receiver. Okay, so in this way, uh, waveguides are useful for us. Apart from being used as an interface between different antenna and receiver or transmitter, they can be interface between different components also, like isolator, directional coupler, or attenuators. So they will be acting like interconnections between different microwave components also. If you see the uh, figure over here only, you can understand that these will look as if the water pipe bends. So to interconnect different pipes, we use bends, right? So similarly, to interconnect different devices, we use waveguides. That is the second application. One is to help the propagation or interfacing between the transmitter and antenna to receiver. Another is like interfacing between different components. Okay, this is about waveguides. So now we'll come to our actual setup. So this is microwave test bench. As I already said, using this setup, we are going to measure different parameters of the microwave signals. So let me first introduce the different equipments we have in this test bench. First one is klystron power supply, reflex klystron power supply. This setup is our test bench, where this one is klystron mount, whereas this is reflex klystron generator. This is a klystron tube which is generating microwave signal. Then this is a cooling fan, because this uh, tube gets heated. Since it operates on a very high voltage, it gets heated easily, and to cool that we have a cooling fan. Then the next component what we see here is called as isolator. It is isolator which isolates the source from the reflected signals. That is, when microwave signal is generated, it is transmitted through the setup. If the load end or termination is not matched, these are two terminations or loads, we can connect anywhere depending on the application. So if they are not matched, the load is not matched, then reflections will occur. So part of the energy comes in the reverse direction, and this will lead to voltage standing waves, correct? And this voltage standing waves may harm the generation of the microwave signal itself, or it might harm the device as well. Both the possibilities are there. That's why it should not reach the source, the reflected energy. So it allows only unidirectional flow of energy, the isolator. Next component we have is variable attenuator. If our signal required at the receiver end is less than what is generated, then we can use this variable attenuator fitted with screw gauge. By rotating this gauge, we can attenuate the signals to a desired level and transmit it into next level. So that is the work of attenuator. Next we have is frequency meter. This is used to measure the frequency which is being generated by this particular reflex klystron oscillator. Okay, so to measure that we are using this because our CROs cannot measure. Why? We are generating a frequency in X band which is between 8 to 12 gigahertz, but our CROs will be rated with 25 megahertz or sometime 20 megahertz or sometime 30 megahertz. So they can measure only the frequencies up to this value. So to measure this value, either we need to have spectrum analyzers with high precision, or we can have some other indirect methods. So this is one of the method. Frequency measurement is using frequency meter is one of the method where resonance occurs for the exact frequency whatever generated. For that frequency, resonance occurs when you go on rotating this meter. Okay, that we'll see in the demo how it shows the particular value. Then we have the moving carriage. This is fitted with a vernier caliper. So this particular arrangement is used to measure VSWR as well as guide wavelength. Okay, and then finally this is a match termination. Why match termination? We are saying impedance matching is there, then only maximum power transfer will takes place, otherwise power losses will be more. So match termination is used. Similarly here, this is having another output. So if you are measuring these two, you will be connecting the CRO probe over here, and if you are not measuring VSWR or lambda G, then you can connect it over this point. So inside this there will be a crystal diode for detecting the signal, the microwave signal. Okay, so now you might be wondering why we have connected signal to a CRO which is a square wave. Since microwave signal 8 to 12 gigahertz is unable to visualize using this CRO, but we are showing a square wave. Okay, so for this there is a reason. Since we are not going to visualize this particular bandwidth of the signal, what we are doing is using this klystron power supply, we are generating a AM modulated signal, amplitude modulated signal. What it does is it will generate a square wave if microwave signal is present, or else zero. So presence of the square wave represents the generation of microwave signal. So this microwave signal is modulating a square wave. Correct? Microwave signal is modulating a square wave. So this square wave is visible over here, and variations in the square wave we can map to our microwave signal measurements, like the amplitude levels, attenuation, then dip in the signal when you are rotating this frequency meter. So using the variations in the waveforms, we can determine different parameters. Okay. Another point I missed to tell is this reflex klystron power supply is having two functionalities as indicated here. One is to supply the power for this microwave generation. Another one is generating the modulating signal for the microwave signal. Okay, so this is the whole setup what we have. Instead of using CRO, we can use VSWR meter also. Okay, this is more accurate method compared to this one, but to visualize the signal it will be better. That's why we have used now CRO. So that's all about the theory part of this particular experiment, you can say. Now let us go through the demo of the experiment. Power supply, then we have a test bench setup. Okay, here this klystron power supply we need to turn on first using this button, then we have to turn it on the HT or high tension button. Okay, now with turning on the switch we are able to get the microwave generated using klystron oscillator, and then it passes through different sections of this rectangular waveguide setup. Okay, this is isolator, this is your variable attenuator, this is frequency meter, and this is slotted section, and finally this is your load. Okay, and the fan should be on when you turn on the klystron power supply or the signal is getting generated. Now you can see the knob at meter select is repeller voltage position, beam current is minimum, repeller voltage is maximum. This is the condition you have to follow. No need to change anything in the klystron power supply, as it is you have to use. Now once the signal is generated, for the part A experiment we are going to measure frequency using frequency meter. Okay, and we are going to see the attenuation by using variable attenuator. As you can see, there is a square wave generated. There is a square wave generated, and this square wave is a modulated signal of the microwave signal. That is, microwave signal is modulating a 1 kilohertz square wave, and that we can observe because our CRO is capable of showing only up to 25 megahertz signals. Okay, since we are generating a gigahertz signal or a very high frequency signal, it is not capable of showing or displaying such kind of signals. We are going to have a modulated signal onto our DSO screen. Okay, now to measure the frequency, we have to rotate this frequency meter in the anti-clockwise direction, such that at some particular point you can see a dip in the waveform which is observed on the DSO. As you can see here, at this point particularly we can observe that there is a dip in the square waveform which is being generated. Okay, so this is the resonant frequency and the frequency being generated by klystron oscillator. Okay, so to observe that, so here there are two rings. In between that, whatever the frequency you are observing, that is 8.76 gigahertz is the resonant frequency, and that has to be taken as your frequency reading. Okay, so that is your first reading of experiment. Now attenuation, you just need to have the observation here. As I rotate this screw gauge in the clockwise direction, it goes on pressing inside the rectangular waveguide, and thereby the available width for the flow of electromagnetic signal will be less, and you can see there is a attenuation of signal. As you can see, it is attenuated now. If I rotate in the other direction, the signal comes back to the normal level. So thereby you can see we can variably attenuate the signal using this screw gauge arrangement or variable attenuator. Okay, that's the first part of your experiment 5. In the second part of the experiment, we have to calculate free space frequency f0. For that we want lambda naught. Lambda naught is the free space wavelength. To calculate that, we have the equation as 1 by lambda naught square is equal to 1 by lambda g square plus 1 by lambda c square, where lambda g is given by 2 into d2 minus d1. So what is d2 and d1? Let us experimentally see what it is. Now we will have to move this vernier caliper in this direction, and you can observe in the waveform that the amplitude level of waveform is increasing. At certain point it start dipping again. So before it start dipping, we have a maximum value. This is our maximum value. Let me show it to you again. Okay, this is your maximum value. At this point we need to take the reading of vernier caliper, which is around 9.34 centimeter. That is your D1. Now continuing in the same direction, you will get a dip or minimum value in the waveform, and again it will goes back to maximum if we continue in the same direction. This is the maximum again. At this point again we will note down the vernier reading, which is around 11.9 or 11.8. Okay, the second decimal can be observed from 0 to 10 coincidences. So this is your D2. Using D2 and D1, now we can calculate lambda G in centimeters. Similarly, lambda C is the cutoff wavelength, which can be given by 2 times A. A is the width of this rectangular waveguide. Okay, it is around, if you measure using scale, it is around 2.3 centimeters. Using that, lambda C is 4.6 centimeters. Lambda C is 4.6 centimeters. Using lambda G and lambda C, we can calculate lambda naught with this equation, and then F naught. Okay, this is in centimeter. This also has to be converted into centimeter, that is 3 into 10 to the power 8 meter per second it is. So you convert it to centimeter, or you will convert this one to meters, then you use and get the F naught. And it should be observed that this F naught is near to 8.76 gigahertz, which is already measured using the frequency meter. Okay, after that, the another measurement we are left with is VSWR, or voltage standing wave ratio. It is a ratio and it is not having any unit. Okay, this you have to observe. So how will you observe the VSWR? VSWR is measured by measuring the Vmax voltage level. This is the maximum voltage level what we can get in this modulated square wave, which is 18.2 millivolt for this experiment. Okay, and if I move the caliper in this direction, this is the minimum value, that is 3.8 or 4 millivolt, approximately 4 millivolt. If Vmax by, that is 18 millivolt divided by 4 millivolt, if I do, whatever value I will get is our VSWR.
Since we use microwave power measurement, we have to consider square root of Vmax by Vmin for VSWR measurement.